All right, today is day 2 on our chapter on probability. Today we're talking about combinations, and then we're also going to squeeze the binomial expansion theorem in here as well. Even though the binomial expansion theorem doesn't necessarily deal with probability, I'll show you what we're talking about, how that is connecting here in the lesson. So, up first we have the definition of combinations. So this is going to tie very closely in with the idea of permutations, which was discussed in the previous video. Remember, permutations is saying, hey, I have n people or n objects, and I'm going to select r of them. However, the order in which I select them with permutations mattered. In the order in which I select them with combinations, it won't matter. I'll give you an example of what I mean. Let's say I have my class of 20 students, and I'm going to give 3 of them $100. Okay? You don't care if you were selected first, second, or third. You're just like, yes, I got selected. I'm going to get the $100. That's an example of combinations because the order is not important. You don't care whether you were first, second, third, as long as you were selected. That's a combinations problem. It would be permutations if I said, hey, first person I say gets 500, second person I say gets 300, and the third person gets 100. Everybody else gets nothing. Okay? That would be permutations because you now care if you were selected first, or if you were selected second, or if you were selected third. There is a difference in your prize. So in that case, order would be important, and that would be a permutation, not a combination. Here's the formula for combinations down here. I'm not going to really expect you guys to need to do this, simply because that's still found in our calculator. The commands, let's say that I have a class of 26. That's the n value, and I'm going to select when order doesn't matter, so it's combinations. I'm going to select 3 of them to give a prize. How many different ways can I do that? First, you would type in the n value, which is 26. Then you go math, PRB, combinations, 3. And you would find out the answer is 2600. Right? Remember, that's math on our calculators. Go over to PRB, and you select NCR. Combinations. A huge part of this is going to be you guys identifying when is it a combinations and when is it a permutations. That's really the tricky part. I'm not having you guys do the calculations. Our calculators can do that. Remember, you guys are allowed to use your calculators on the ACT and the MCA. So what I'm really going to be quizzing or testing you on is saying, hey, do you guys know the difference between combinations and permutations? Remember, what you're asking is, does the order in which the winners are selected make a difference to the winners? Okay. Another example. Let's say we are playing heads up, 7 up. Okay. I'm going to select 7 of you, Susie, Johnny, blah, 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 right? It doesn't matter if I select students in A, B, C, D, E, F, G order, or however many students there are, or if I select them in the reverse of that order. All that they care is that they're selected. It's going to be the same group of 7 students up there, right? So that makes it a combinations, because the order in which those winners, those people that were selected, did not make a difference to those people. So that would be an example of combinations. So here are 4 examples that we can talk about. In a lottery, 4 winners will get equal prizes. That idea of the equal prizes is the deciding factor, right? If 20 people enter the lottery, how many different groups of 4 winners can be chosen? Hopefully you guys are in agreement with me that this would be a combinations example, right? The idea is you don't care if you were the first of the 4 selected, or the third, or the fourth, you're getting the same equal prize, so this is combinations. What about how many ways can 11 books be arranged on a shelf? The idea here in the deciding word is going to be this word arranged. Arranged is a huge hint that we're discussing permutations, not combinations. Because the idea is, if I switch books 2 and 7, I have made a new arrangement. Therefore, the order matters, and this would be a permutations problem. More specifically, if you're thinking back to 10.1 where we discussed factorial, if I have 11 books and I'm selecting all 11 of them, which I am here, this could be solved with a simple factorial. Okay, I have 11 books and I want to know how many ways I can select all 11 of them in which order is important, right? Because if I switch the order, I have made a different arrangement. So that would be factorial. I could also do 11 permutations 11. Those would be the same answer. Now if I said, hey, I have 22 books, how many ways can I arrange 11 of them on a shelf? Then that would be 22p11, and I couldn't use factorial to do that. Factorial only works if you are selecting the same number of items as you have. Not when you have 22 of the item and you're only selecting 11. Then you have to use permutations. Next example, the top 3 finishers in a race qualify for nationals. How many different groups of 3 finishers are there of the top 12 athletes competing? So 12 athletes are racing. I'm going to select 3 of the top 3 are going to go to nationals. Okay? This is a combinations problem. You don't care if you're the first or the third. Maybe you do care, but it's not a different group of students going to nationals. Okay? And that was the question. How many different groups of 3 students are there? It doesn't matter if it's A, B, C that are chosen, or if it's C, B, A that are chosen. It's the same group of 3. Order doesn't matter there, so it is combinations. And then last example, a committee of 15 people will need to select a president, a vice president, and a secretary. How many different possibilities of elected officials are there? Anytime where we have committees, I could go either way, right? I could say, how many different ways are there to select 3 people from a group of 15 to be on a committee? That would be combinations. But here, I'm giving them distinct roles. I'm saying, hey, one is president, one is vice president, and one is secretary. If I now move the secretary to president and the president to secretary, I've made a different group. I've made a different committee, right? And so this would be a permutations example. The idea is I've made a distinction between those people that are selected. And so that's what tells us that it's permutations. That's all we got for combinations and permutations today. Up next, I'm going to talk about this binomial expansion theorem. And so the idea is we are going to take binomials, okay? Binomials, remember, have 2 terms, hence binomial. And we are going to take them to some power. In this case, to the 3rd power. We've discussed how you guys have the urge to take that to the 3rd power and apply it to both terms, and that's not the way that we can do this. That will always lead to the wrong answer. Instead, remember, what it means to cube something or to take something to the 3rd power is to multiply it by itself 3 times. And then what you would do is you would FOIL 2 of them together and you would get that answer. And then you would combine like terms if there were any. And then you would take that and you would multiply it by the 3rd one. And in today's lesson, I'm not just going to be limiting to the 3rd power, which is I think all we've done so far. But I might say, hey, what is it to the 6th power? And then you would, if you were going to do that, you would need to write it out 6 times. And then you would multiply 2 of them at a time until you only had one set of parentheses until they were all combined. Now we're going to learn another way to do that, and that's a good thing that we're not doing that, because on the test, I believe I say, hey, what is the given term of something to the 20th power? Now imagine doing that 20 times. I can't. It would be miserable. Okay? So we are going to learn a different way to do that. The bad news is it isn't necessarily easier or less time-consuming. It would be if it was to the 20th power, but if I was taking something to the 3rd power, it would be easier for me to just expand it and multiply it out. like I have shown. But we're going to learn another way to do it. Sometimes it's going to be quicker, sometimes it's not, but you guys will need to know how to do it regardless. And this is the way that the book lays it out, and notice that it's got combinations here. Okay? It uses combinations in the formula. Hence, why we have attributed it to this section in probability. Now, I'm not going to ever use it in the sense of combinations, but I'm just showing you this to point out, hey, this is why it's in 10.2, even though it doesn't really have anything to do with probability. Instead, how I'm going to talk about it is using Pascal's Triangle. And Pascal's Triangle has multiple different uses in math, and you'll see it in a lot of math classrooms. I have it up in my classroom right now on the whiteboard, and I'm going to leave it up through this chapter so that you guys can use it whenever you need to. When we look at what Pascal's Triangle is, okay, it's just the number 1 up at the top. Because you guys, like I said, I'm going to have it up on the whiteboard, but you guys should know how to create it. And if this was ever on some standardized test, you would need to be able to create it. So it's 1, and then the second row is just 1 and 1. And then how you proceed on every row below is you take the numbers above it, and you add them together. So 1 and 1 would make 2, and that will go in between them. Ones will always be along the diagonals, like this. Whoops. There we go. So then that would give us 1, 2, 1, and then we would take these and we would add them to get 3. We would add these to get 3, and then ones would go on the diagonals again. Add these to get 4. Add these two things together to get 6. Add these two together to get 4. And then ones go on the outsides. And we could keep creating it that way, right? Right now we've got this row. We could add 4 and 6 to make 10. Add 1 and 4 to make 5. Add 6 and 4 to make 10, and so on and so forth. So that's Pascal's Triangle. Now how do we use Pascal's Triangle to expand a binomial? Let's go back to this example just because it's an easier one. What you would do to expand this binomial is you would see that it's taken to the third power, and so you would go to the third row of Pascal's Triangle. Now, just so you guys know, when we're referencing this, the top row is actually called the 0th row, first, second, and then third row. The third row is going to be the one with the number 3 in it. We get the digits, or the numbers 1, 3, 3, and 1. So I'm going to go back to my example, which is this guy here, and I'm going to space out the numbers 1, 3, 3, and 1. Now, after each number, I'm going to put, this is my A term, and this is my B term. So I'm going to take A, which is 2x, and I'm going to put that in parentheses after each of the numbers that I just got from Pascal's Triangle. So I have 2x, and then 3, whoops. 2x, and then 1, 2x. And then I'm going to do the same thing with the b term. I'm going to write that right after each of the numbers in red that I just wrote, each of the a terms. So it would be y, 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 and y. This is exciting, I know. Now, to the first term, which is this, or to the a term, the first a term, this 2x, I'm going to take it to whatever power my exponent is. So I'm going to take the first one to the third power, and the next one to the second power, and then to the first, and then to the 0. And then the y, I'm actually going to just do the reverse of that. The first one I'm going to take to the 0th power, and then 1, and then 2, and then 3. So you'll notice that my exponents always add up to 3. Okay? Which is the exponent I'm taking it. 3 and 0, add up to 3, 2 and 1, 1 and 2, 0 and 3. Basically, I started with 3 and 0, and then I sent one over the next time. So then it was 2, 1, and then I sent another one over, 1, 2. I'm going to continue this in the next video, so join me there and we'll solve this problem in a few more.